Good morning. I realize that I'm the last speaker before the lunch break, so I'll try and make this relatively quick and get us all out to lunch. This presentation is based on some work that was done for the IETF Traffic Engineering Working Group. We produced a best current practice document that documents how Cable and Wireless does traffic engineering on our IP backbone. I'm going to go over the materials presented in that best current practice, as well as some of the background material to that, and then I'll open it up for questions. If anyone has any questions they don't ask here, my email address is on the slide, and you can feel free to send me an email. So, again, the scope of this is to present how C&W does traffic engineering and some of the reasoning behind it. This is not the one true way, no matter what some people might think I believe after private discussions, but this is the way that works for us, and we've been fairly successful using it for a number of years. Originally, Cable and Wireless, at the time Internet MCI, was one flat layer of routers on its network, and that was through 97, 98. 96 or thereabouts, the DS3 direct router-to-router circuits were replaced with OC3 ATM circuits, and the routers were completely meshed over an ATM core. So every aggregation router on the Cable and Wireless network was meshed to every other router on the Cable and Wireless network, on the Internet MCI network at the time. Then in 1998, we had a network event. We added 6 or 8 more routers somewhere in Chicago. I'm trying to remember if it was Willow Springs or Downers Grove. But it was enough to push the poor 7000s at the time, Cisco 7000s, over the edge as far as IGP calculations, and we had a complete IGP meltdown. It was an educational experience. It was an educational experience that lasted about a week as we rebuilt the network and got everything stable again. At that point, we decided that we needed to add some hierarchy to the network to reduce the flat IGP mesh. At the time of the event, there were over 380 routers in the mesh, accounting for approximately 30,000 PVCs in the network, and each router was maintaining approximately 760 direct IGP associations. Again, very flat, not a lot of traffic flowing over those IGP associations or routing information because every router was directly meshed, but still a little bit too much for the 7000s and earlier 7500s to keep up with. First bullet point is the same as the last bullet point on the last slide. I must have been doing this on a plane or something. Currently, since 1998, we've added a level of hierarchy. So now aggregation routers, I should have a diagram up here and I don't, I'm sorry. Aggregation routers in a POP are meshed with all the other aggregation routers in a POP, as well as the core routers in a POP. And then the core routers in each POP are meshed to every other core router in every other POP. So we have a two-level mesh, fairly common today. That means that for us, there's no more than 80 routers in each in any particular IGP mesh. One of the things that we do, and I'll get into this in a minute, is we do calculations of all of our traffic engineering layout offline. So before we added the layer of hierarchy, it was taking us approximately 4 hours to calculate the traffic engineering layout of the network using some homegrown tools. With the decrease of the diameter of the meshes, in discrete meshes, that time's gone down to about 20 minutes. We've also done some software optimization, but the big thing has been going from meshes that calculated 380 routers in a mesh to meshes that calculate no more than 80 in a particular mesh. The one thing on that hierarchy as well is we do run two-level ISIS. The core routers sit in level 2, and each POP, the aggregation routers and core routers in each POP sit in level 1. So the core routers are the level 1, level 2 meet point. Online versus offline. Cable and Wireless is an offline traffic engineering shop. We do our traffic engineering offline. We don't allow the routers to do it in normal or even in most failure scenarios. We like to know where our traffic's going. And like I said, calculating optimal networks on our software today still takes approximately 20 minutes to lay out a complete network with both primary and backup routes. That's on dedicated hardware, using dedicated resources. We believe that doing that online and taxing processors to do that online, you're not going to be getting optimal solutions, or your solutions may be changing over time as resources come and go on the network. We'd much prefer to do this offline and pre-plan all our primary and backup routes. We also do traffic engineering, so we do it offline, and we do it at layer 2, not layer 3. Utilizing IGP metrics, as some other people have mentioned here, to adjust traffic flows on an IP network lead to a network-wide and sometimes usually unplanned effects on a large network due to flooding. I.e., if I adjust a metric on one link to steer traffic from, say, Chicago to New York over a different set of links, I might have the unplanned consequences of pulling traffic from LA to New York over those links as well, unless you're very, very careful. The equivalent for those of you who have ever gone to county fairs or state fairs is the midway game, where you take a mallet and you hit the head of a groundhog that pops out of a mechanical groundhog that pops out of a hole, and as soon as you hit it, another one pops up somewhere else. It's a similar effect when you start playing with IGP metrics on a very large network. As you adjust metrics in one place to resolve a local problem, you create problems in other localities. So our belief is we'd prefer to lay out the traffic flows at layer 2 and use IGP simply for link failure detection. In our case, we use our IGP ISIS only for link state signaling and in normal and most failure mode scenarios. So every element on the network has at least 2 paths laid out over separate layer 2 paths to get to every other element on the network. Either it's core router or another aggregation router, or between core routers. Therefore, ISIS simply indicates if the link is available. It's really not used for routing. The only time it would be used for routing is if both the primary and backup links went away due to 2 different failure mode group failures, where we lost both the primary and backup resources, at which point IGP would be used to find a multi-hop route to the destination on the network. But that has very rarely happens on our network. I could probably count, since I've been in cable and wireless 3 years, I could probably count in one hand the number of times we've actually had multi-hop failures. One of the things is our metric deployment. We really only use a small subset of metrics. Because everything has direct adjacencies, we really only use 2 metrics on the network, one to indicate a primary path, one to indicate a backup path. We do bias certain links as expensive, so in case of a multi-hop failure, we do end up using local resources rather than global resources to restore that failure. So the example would be, we might use a metric of 5 to indicate a primary route between Chicago and New York. We might use a metric of 10 to indicate the backup route, and we might use a metric of 20, say, to indicate for all links going over the ocean, which would prevent traffic going from Chicago to New York if it lost both the primary and backup route, would pick another set of routes
in the U.S. rather than tromboning over to London and come back over the global mesh. So things that add long latency or that are valuable resources we tend to protect with slightly higher metrics in case of a double failure. Next is what we're doing for our Layer 2 traffic engineering mesh. Since '96, it's been ATM. It's been ATM until last year when we started a migration to MPLS. And the reason we migrated to MPLS was ATM over PVCs. ATM with PVCs is the traffic engineering mesh. Worked quite nicely, except for the ATM overhead, and except for the lack of high-speed router interfaces. And there are some others in there, but all in all, we had no problems with using ATM. It worked. It was a handy tool. But the lack of anything faster than OC12 interfaces on routers and the overhead on some expensive links became a problem. So we actually then started looking for alternatives and settled on MPLS as probably the most reasonably supported solution from our vendors to replace ATM. We do treat it as basically, in the traffic engineering core, there's actually two separate MPLS networks at Cable and Wireless. One network is a network that provides MPLS-based services, i.e. MPLS VPNs, Layer 2 and Layer 3 VPNs. And then there's the MPLS traffic engineering core. We do not allow those two networks to touch. The MPLS service network actually rides over the traffic engineering core, and I can talk to people offline. It's a little bit too in-depth to go into here, the time remaining. The MPLS traffic engineering core is really treated as simply an IP-friendly ATM. Actually, it's more like frame relay. And in fact, I use frame relay resources. I use frame relay signaling to access that MPLS core. We actually use CCC, and we'll be using Martini and CAP later to access the MPLS core. That way the IGPs of the MPLS core are not shared with the IGPs of the IP network. They're two distinct IGPs. That way a failure of, or a flap in the IGP network, the IP network, an IGP flap in the IP network, doesn't destabilize the traffic engineering core and lead to one unstable network trying to recover onto another unstable network. So we actually use a PVC-like signaling, in this case DLCIs, between the core routers and the traffic engineering switches, the MPLS switches. So the IGBs are between the two networks are totally disjunct. Will Lambdas replace MPLS in the cable and wireless network? The only time this would really happen, we would consider this, would be when the bandwidth required for any router-to-router pair approaches the bandwidth available from a single lambda. So until a core router-to-core router flow, say again, in this case, London to New York or Chicago to Washington, approaches 10 gigabits, there's really no reason to use lambdas to act as a traffic engineering layer rather than MPLS. And in fact, there's some disadvantages to doing it, namely that for each lambda you need very expensive router interfaces and router space on the router to place those interfaces. So if you're talking about a fraction, the core router to core router flows being a fraction of a lambda, it makes more sense to aggregate at the MPLS label level rather than at the lambda level. The other is the cost of a port on an OXC would need to be significantly cheaper than the equivalent bandwidth port on an MPLS switch. That's probably a reasonable argument you could make today. But both of those things have to occur before we would consider replacing MPLS with a DWDM-based traffic engineering layer. When that occurs, we would provision lambdas just like we do the MPLS LSPs on our network today. i.e. they would be statically laid out, and they would be statically signaled, static and offline laid out. We would also make sure we would add resilience, etc. GMPLS may be the technology we would use to signal those LSPs and those Lambdas, just like MPLS is used to signal LSPs today, but we would not see merging the MPLS network and the GMPLS network together. Those would still be disjunct entities. Tools. Currently, the tools that we use to complete the paths and that configure the Layer 2 and Layer 3 equipment with those configurations are all developed and maintained in-house. We do check some accuracy using tools like OpNet and Wandle and some of the other network modeling tools, but the actual devices that we use to measure to measure the traffic flows and to actually lay out the paths are all in-house tools. Some of them have been in development for over 6 years, a continual development tweak cycle. And some of you who have originally were at Internet MCI and have now moved on to other places would be happy or horrified to know that ATM Gen still exists and is still being actively used today. So, futures. Today, because we run ATM as a static entity, failures are detected at Layer 3, i.e. at the IGP level. So if we lose an ATM link today, IGP detects that and selects the backup route. With MPLS, we are looking at doing that at Layer 2 rather than Layer 3, which should speed restoration times significantly. To do that, we are looking at signaling with RSVP to set up the LSPs, a strict route signaled LSP. However, we do not plan on using the resource reservation characteristics of RSVP. The network will continue to be set up completely offline, and there will be no bandwidth reservations for the individual LSPs. The bandwidth reservations will take place in the offline tool, and the traffic will be laid out using the offline tool with 0 megabit per second or gigabit per second reservations on RSVP. So there will be no bounding on the LSPs. The LSPs will be allowed to burst to whatever diameter they need to reach, and we will continue to deal with that statistically offline rather than allowing the network to deal with that dynamically. Path redundancy, we believe, will grow from 2 to 4 paths per router pair, making use of multiple paths per LSP, again, as a restoration mechanism. We would prefer most failures to happen without the IGP, Layer 3 IGP, the IP IGP, realizing there's been a failure. So we will probably end up going to 4 paths instead of 2 to give us complete resiliency across the entire network while trying to hide as many of the failures from the IP network as possible. Some of the things we are looking at to better optimize our network layouts and speed our network layout times is there have been some developments in optimization mathematics for circuit path layout on circuit boards and analog circuit design that we believe could be useful for laying out, solving the network path optimization problem. And we will be investigating those as possible algorithms to deploy in our tool in the future. Some of the other things is today this traffic engineering core only handles public IP internet backbone, i.e. AS3561. This traffic engineering core, though, is not necessarily limited to just carrying IP traffic. As an MPLS-based core that uses DLCIs to ingress to it, we could theoretically layer other services on top of this, i.e. an MPLS service network, which would offer VPN services. Technically, even voice over MPLS or other services that we might eventually decide to put over the traffic engineering core and share one common set of resources could be laid over this network with no impact. And that's the end of the presentation. So I thought I'd, at this point, open up for any questions.
Hi, my name is Bill Norton from Equinix. I really enjoyed your presentation. I found it interesting, for one, that the offline approach was used for you guys. I'm curious first, how often do you do that process and make the adjustments on your network? Maybe you said it and I just missed it.
Sure. Sorry about that, guys, for popping the mic. We normally do our bandwidth layouts about every 6 months or thereabouts. So it normally happens a couple times a year. If we have a significant loss of resources on the network, say like loss of a whole undersea cable system, we may do a tactical redesign of the network, because usually undersea cable systems take weeks to fix. But in the case of a terrestrial cable's failure, we usually don't replan around that because those are usually fixed in terms of hours or a day or two. So the network is usually replanned at about a 6-month interval unless there's a major hit somewhere.
So I'm guessing the utilization is relatively low of the bandwidth that you have available?
The utilization, we actually, because we've been running a traffic engineered core for about the last 6 years, I have 6 years worth of trend at a couple minute intervals for every router-to-router pair on the network. So I have fairly good statistics on growth patterns, say of traffic from New York to Chicago or from London to LA, that I can draw upon and basically plot curves out to, say, 9-12 months in the future, factor in any market conditions. So really, we plan every 6 months, but we use bandwidth requirements for about a year out at every 6-month planning cycle. So we're always a period or two ahead of ourselves.
Okay, and then one last question because there are people behind me. Then we can chat offline afterwards. The analysis you made about router-to-router pairs and the 10 gigs being sort of a point where you would prefer to use wavelengths. I was curious if that was simply a financial analysis, or is that really a broader analysis than that? Is it a price per bit point you're hitting?
It's more than a financial analysis. If you're only going to be flowing a gig or 2 gig or 3 gig across the link between two router pairs, why drop to one expensive 10 gig interfaces on your MPLS traffic engineering switches, and 2, why waste the front panel bandwidth or the front panel capabilities of that box? You can only put so many interfaces on that box, and it's much better for you to try and pack as much bandwidth into that available real estate as possible. Otherwise, you're going to be forklifting that box earlier than you even do now. Yes?
Hi, I'm Escure from Dante. The fact that you are doing everything offline...
Could you speak up, please?
Sorry. The fact that you are doing everything offline, does it mean that you have only explicit LSP?
Yes, explicitly routed LSPs.
Right. Then, in case of failures, then do you have explicit backup LSP, or how do you manage that?
We basically have 2 explicit LSPs, each made up of 2 explicitly routed paths.
Thank you.
Mm-hmm. Yes.
Just a clarification first, and then a question. Today, your explicit routed LSPs, are you using RSVP to set them up, or is that all set up statically also? They're
using RSVP to be set up.
And as you're looking into reroute at layer 2 instead of IP, are you looking at local repair versus end-to-end LSP repair? And have you looked at the detour versus facility backup proposals?
We're looking at what could best be termed regional repair. So I'm not looking at local repair or fast reroute. What we are looking at is basically end-to-end repair, but the ends may not be the entire end-to-end of the network. It may not be the origination and destination IP router. There may be multiple LSPs stitched together along the path to give me a restoration time of a certain number of milliseconds in signaling. Any other questions? Thank you very much.